This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're exploring a fascinating paper claiming experimental evidence that a photon can spend a negative amount of time within an atom cloud. Sounds paradoxical, doesn't it? Let's delve into the details. What's the core concept being investigated here?
The paper investigates the time a photon spends as an atomic excitation while traversing a medium. Intuitively, one might expect a positive time delay, but near atomic resonance, the group delay, the overall time delay of a light pulse, can become negative. This challenges our understanding of light-matter interaction.
So a negative time delay. How is that even possible? Is it a purely mathematical artifact, or does it have a physical interpretation?
That's the central question. The researchers argue that the negative group delay isn't just a mathematical quirk. It reflects a real physical process. They use a clever experimental setup to measure the time atoms spend in an excited state due to a transmitted photon.
Can you explain the experimental setup? It sounds quite intricate.
They use a two-beam system, a resonant signal pulse, and an off-resonant continuous wave probe beam. The signal pulse interacts with the atoms, causing excitation. The probe beam, interacting via the cross-Kerr effect, measures the degree of atomic excitation. Crucially, they post-select on transmitted photons.
Post-selection, what does that mean in this context?
They only consider events where the signal photon passes through the atom cloud without being scattered or absorbed. This post-selection allows them to isolate the effect of the transmitted photon on the atomic excitation.
And what did they find? Did their measurements confirm the possibility of negative time?
Yes, their results are consistent with theoretical predictions. They measured mean atomic excitation times ranging from negative values, for narrowband pulses, to positive values, for broadband pulses. The key finding is that the mean atomic excitation time equals the group delay, even when negative.
This is counterintuitive. How do they explain the negative time? Is it a violation of causality?
No violation of causality. The negative time arises from quantum interference effects. The paper provides a detailed theoretical explanation involving quantum trajectory theory and the weak value formalism. Essentially, the negative time reflects the interplay of different quantum pathways.
So the negative time isn't about the photon traveling backward in time, but rather a consequence of quantum interference?
Precisely. It's a consequence of the wave nature of light and the way different frequency components interfere.
The paper mentions a previous experiment with similar findings. How does this new work improve upon the previous one?
The previous experiment was limited to a single set of parameters. This new study expands the parameter space, investigating different pulse durations and optical depths, providing stronger evidence for the phenomenon. They also improved their experimental techniques to reduce noise and spurious correlations.
What are the implications of this research? Does it have any practical applications?
The findings have implications for our fundamental understanding of light-matter interaction and quantum optics. It suggests that the group delay, even when negative, is a physically meaningful quantity, reflecting the interaction of photons with the medium. Potential applications could be in quantum information processing and quantum technologies.
The paper also presents an alternative explanation using the AC Stark shift. Can you elaborate on that?
Yes, they showed that the phase shift on the probe beam, which is what they measure, is directly related to the group delay through the AC Stark shift induced by the probe on the signal. This provides an alternative, more intuitive way to understand the connection between the measured phase shift and the group delay.
So this alternative explanation reinforces the main conclusion that the group delay, even when negative, is physically meaningful.
Exactly. It provides a different perspective on the same underlying physics.
What are some of the limitations or challenges in this research?
The measurement is extremely sensitive, requiring sophisticated techniques to minimize noise and spurious correlations. The negative time values are small and require careful analysis to distinguish them from noise.
This has been a fascinating discussion. Thank you for explaining this complex research in an accessible way.